Hey everyone. So as you can see, we're going to talk about the connection between derivatives and continuity. Okay, so the first thing, let me just state it, is that, and I'll show why in a second, if f of x is differentiable at a point A, then f of x is continuous there. Right? So in other words, differentiability implies continuousness or continuity. All right, so let's just prove this, okay? So suppose f of x is differentiable at x equals a, right? So to prove this, I just need to show that if the first half of this claim is true, it necessarily means that the second half of this sentence is true, right? So if I have the if part, I must have the then part. So suppose f is differentiable at x equals a. This means the limit, as we're going to use the other definition. Let's use this. The limit as x goes to a of f of x minus f of a over x minus a exists, and it's equal to the number that we can write as f prime of a. I don't need to know what this number is. I just know that it's there. Since it's differentiable there, this limit exists. It goes to some number, and the symbol I'll use for that number is f prime of a. So we need to show that with this information, f is continuous at a, which is to say the limit as x goes to a of f of x is equal to f of a. So let's consider that the limit as x goes to a of f of x is equal to the limit as x goes to a of f of x minus f of a plus f of a. Okay, so this is just a number, right? F of a is just a number. And I've added and subtracted this number, so I've done nothing. I've added 0 to this thing, right? So I can do that. I haven't changed what what we started with f of x. We still have f of x. We just have the 0 there written in a funny way. Okay. So I'm going to use the limit laws. The limit as x goes to a, and I'm going to split this into two different parts, f of x minus f of a plus the limit as x goes to a of f of a, right? So really what I did here was I grouped this sum in this way, and then used that limit law that lets me split up over a sum. Okay. Now, the reason I grouped it this way is I'm going to do something interesting to this first parentheses. I'm going to multiply, let me make these parentheses a little bigger. I'm going to multiply what's in these parentheses by 1. Okay. But the way I'm going to multiply it by 1 is by dividing by x minus a and then multiplying by x minus a, right? That won't change anything because we're multiplying by 1. But dividing my number and multiplying by it works out, right? This would be problematic if x could be equal to a, but if the limit doesn't care. The limit looks at all the points where it's not equal to a. So this is a perfectly valid thing to do. It doesn't change the value of what's in there. So we've employed this trick now twice now of we want to manipulate things, but we can't change their value. So the first time we added 0, now I'm multiplying by 1. Now I'm going to use my limit laws again. I'll get the limit as x goes to a, f of x minus f of a over x minus a. Limit as x goes to a of x minus a plus, And this limit we can take. This is the limit of a constant. F of A is a constant. A is some number, so F of A is some number, and the limit of a constant is just that constant. So this limit at the end is done. That's just F of A. Well, what do we have here? This first limit we know exists. That was our assumption from the beginning. We have a function that's differentiable at A, and there you go, there's the derivative at A. So this whole red box can be written as F prime of A. This next limit, the limit as x goes to A of x minus A, that's a polynomial, right? Degree 1 polynomial, linear function. And we can just plug in the value A into x, and we get A minus A is 0. So we end up with F prime of A times 0 plus F of A. This is, of course, 0, any number times 0, and we're left with F of A. And so this, we've now shown that the limit as x goes to A of F of x is equal to the value of the function there. So F of x is continuous at x equals A, okay? So we've shown that if all we know about as a function is that it's differentiable at A, we must then know that it's continuous there, okay? But what does all this mean, right? We did some algebra tricks. It popped out what we wanted. That's great. We can use this. We know this now. We're allowed to use it. But why exactly is that the case? Well, let's try to build just a bit of intuition about why this might be true. Let's imagine we had a function that was differentiable but not continuous somehow, right? We've shown algebraically that that can't be the case, but let's pretend that we didn't know that. Like, what would happen? Well, if F prime of A exists, it must be the case that F of A exists. Our function is defined there. So our discontinuity can't be an infinite discontinuity, right? To compute the derivative, you need to have F of A. That's part of it. And so it's implied that the function's derivative, the function exists there. So that means our function must have like maybe a jump discontinuity. So maybe our function does something like this, right? Some kind of jumping. Okay. Well, remember what the derivative is doing, right? We're looking at slopes of secant lines, right? So here's my point A, F of A. In order to compute the derivative, right, remember what we do. We pick some points that are nearby and we draw secant lines through that point. Then we pick another one that's nearby and draw a secant line through that point. And if you look at this picture I've drawn, you can see, okay, those have some slopes. And as I get closer and closer to that, they might be approaching some notion. But what happens on the other side where there's this jump? If I draw a secant, let's do a different color for these. Okay. If I pick a point over here and draw the secant line, and then I pick the point over here and draw the secant line, and I keep getting closer and closer, I'm getting infinitely close to that point that has a hole, right? And that's right above, right? The end of the function and the point up here, that jump discontinuity is directly above. So these lines are getting increasingly steep, and there's no limit to how steep they can get because I can get as close as I want to that perfectly vertical line. In other words, the limit of the derivative as we approach from above, if we tried to take this derivative, would have to be approaching, well, the way I've drawn it, negative infinity. I could have drawn it a little different and we'd get a positive infinity. But that limit has to break there on one side, right? I mean, we're just using intuition to prove that, but I think it's pretty straightforward there. So we tried to assume that our function was differentiable and continuous and discontinuous, but it led us to a contradiction that the differentiability can't actually happen, right? A similar thing would happen if we had a function with a hole in it, right? It would have to be defined here. That was one of our assumptions, or one of the things, if we know it's differentiable, it has to be defined there. But the same thing would happen if we started drawing secant lines through points near x values near A and the value of and the function there. There's a secant line. As we get closer, our line is getting as close as we want to perfectly vertical because that hole is right below it. And so as we approach that line, as our points are getting closer and closer to that hole, that line is getting almost perfectly vertical. And the limit, the derivative limit, would have to shoot off to positive or negative infinity, depending on exactly how this curve was drawn. And so we can't have differentiability and discontinuity. Okay. So this is great. So if you have a function and you know it's differentiable, you already know that it's continuous. If you know it's differentiable over some interval or over its whole domain, then you know that it has to be continuous there. What about the other direction? All right, so we just showed that differentiability implies continuousness, continuity. Does continuity imply differentiability? Let's examine this with an example, because it turns out the answer is no. This is not true. Okay, so I want to put that up front so we don't get confused, right? In other words, this is one way we can think about this: differentiability is a stronger condition on a function. If you're differentiability, you automatically get continuity. Continuity, you could be differentiable, you might not be. So let's look at a function that has this condition, a point where it's continuous but not differentiable, and this will help us start figuring out why things might not be differentiable. So here's a function, f of x is equal to, I'm going to look at a piecewise function, x squared minus 1 if x is less than 3, and negative 2x plus 14 if x is greater than or equal to 3. All right, so let's consider these two functions, this function with these two pieces. Okay, first of all, both pieces are polynomials, and we know that polynomials are continuous on their whole domains, right? So these pieces above and below 3 are going to be continuous in all those points anyhow. The only point where we might have a problem is where they connect, right? We've got a parabola, some kind of parabola shape, and then we've got a line, and the question is, do they line up or not? Does it look like this, or does that line connect right there and continue on without having to have a jump? Okay, so we can check this. Let's go ahead and show that this is continuous. We know that to be continuous, we need to look at the value of the function and the limit. We need to look, is the limit as x approaches 3 of f of x equal to f of 3? Well, let's just compute this. F of 3 is a bit simpler. So if x is greater than or equal to 3, we use this linear part of the function. So we're at 3, so we're using negative 2 times 3 plus 14. 14 minus 6 is 8. So the value of the function is 8. Let's look at the limit. We have to look at the limit from either side because different things are happening on each side. So the limit of f of x as x approaches 3 from the left, from below, means we're putting in numbers that are less than 3. So we look at the top part, the top definition here. And so we're getting the limit as x goes to 3 from below, x squared minus 1, but it's a polynomial. I can just put in 3, so I get 9 minus 1, or 8. Similar from above, because now we're putting in numbers larger than 3. We're going to use the negative 2x plus 14, but we know to evaluate this limit, we also just plug in 3, which we just did a second ago, and that's 8. And so these two conditions, the fact that the limit as x approaches 3 from above and below both equal 8, means that the limit as x approaches 3 of f of x is equal to 8, which happens to be f of 3. So we've got continuity. There, I'm checking it off. So we've got continuity. Okay, let's look at the derivative. Okay, So let's look at the derivative at 3. We want to compute f prime of 3. This is the limit as h goes to 0, f of 3 plus h minus f of 3 over h. Okay. Now, let's put in for f of 3. We already know what that is. That's 8. So let's just make this a little simpler. Here's the complicated part. We're taking the limit as h equals 0, and we need to imagine approaching h from both sides, meaning h is representing these tiny numbers that are close to 0. Some of them are going to be negative and some of them are going to be positive. Okay, so so if h is negative, 3 plus h is below 3, and we have to look at the top definition. If h is positive, the values we're putting into f are above 3, and we have to look at the bottom definition. So again, we're going to have to look at this limit in two directions. So let's start with the limit as h goes to 0 from below of f of 3 plus h minus 8 over h. So this is going to be h is below 0. It's negative, so 3 plus h is less than 3. We have to look at the x squared minus 1 definition. So we're going to have 3 plus h squared minus 1 minus 8 over h. Limit as h goes to 0 from below. So we square this, we're going to get 9 plus 6h plus h squared minus 1 minus 8 all over h. What happens? Well, we've got this 9 and the -1 and -8 are all going to cancel out. We've then got a factor of h in the numerator that we can factor out. We get h times 6 plus h over h. These cancel. And we've got the limit as h goes to 0 from below of 6 plus h, which is just equal to 6. So the limit from one side is 6. On the other side, we have to look at the other definition, the other part of this piecewise function, because now since h is above 0, it's positive. 3 plus h is going to be bigger than 3, so we use this linear definition. So I'm putting in 3 plus h into the negative 2x plus 14, and we're going to get minus negative 2x plus 14 all over h. We do a little algebra. I've got negative 6 minus 2h oh, sorry, I wrote the wrong thing here. I knew something was wrong. This is minus our 8. Sorry about that. All right, so now I've got negative 6 minus 2h plus 14 minus 8 over h. Well, my minus 6 plus 14 and minus 8 are 0. I've got negative 2h over h. I've got negative 2. The limit as h approaches 0 of negative 2 is simply negative 2. So this derivative limit, our definition of the derivative at the point x equals 3 here, we looked at the two one-sided limits. They don't match, which means this does not exist, right? And remember that part of the definition. This is the derivative provided the limit exists. If it doesn't, the function is not differentiable there. And that's the problem we have. There is no derivative at 3. So here we have a function that's continuous, but not differentiable. So differentiability tells us we have continuous, have continuity. Continuity does not mean we have differentiability. You can, but it's not a guarantee. Let's look at a picture of this function to understand this a little better. Here's our function, this piece of the parabola and the line. We saw that they're both going from both sides. These two pieces of the function both lead our function to the output 8 as we get closer and closer to x equals 3. But we have this corner there, right? remember what one of our intuitions about derivatives is it tells us what line to draw that will look very much like the function. This is really difficult to do here because from the left side, I want to draw a line like this. And from the right side, I want to draw a line that's just a continuation of that line, right? To match those functions. Those two lines are at odds with each other. Or if we try to draw something in the middle, you know, like let's pretend we've defined something like the average of those two lines. That doesn't really look like the function at all. And no matter how close I zoom into that function, it's always going to be a point with this line, and it's not a very good approximation. That line is doing something very different than the function there. And so there's no way to get around this idea and come up with a line that will be a really good description of what the function's doing there. It's doing something very strange there relative to derivatives, right? It's not continuing in a similar direction. It's making an abrupt turn, right? So, you know, when we talked about continuity, one of the things we talked about was that continuous tells us the function doesn't do anything surprising. If it has a value at some point, we know that nearby the values are going to be kind of the same, right? They can move, but not too much. Differentiability adds to that. It's not surprising in an even stronger way. Not only are the values supposed to be nearby, right? The values here are still nearby. If we look at those values of the red line near that point, they don't move too far away. But with differentiability, not only are they continuous, they're staying in the same neighborhood of value, they're moving in almost the same way. You don't have an abrupt turn. If you want to go from one direction to another, you have to take a slower, you know, curving turn to make that happen, as opposed to abrupt change. If you have an abrupt change, you will have this corner, and the derivative won't exist. It turns out this will mean the derivative itself is not continuous there, right? If I look at this function, for instance, we can imagine what a graph of this the derivative of this function might look like, right? If I approach this point from the left, my values look to be positive, right? So the derivative, if I'm just going to graph it a quick little sketch graph, the derivative values as we approach that look like they're positive and getting more positive. So our graph might be doing something like that. But when we get to x equals 3, the derivative doesn't exist. When we look on the other side of x equals 3, all of a sudden, we have this negative sloping line, right? We know this one's -2. And so there's this jump in the derivative at that corner. It goes from a positive to a negative slope without having passed through all the values in between, okay? So that's an example of how we can be non-differentiable, and in this case, being non-differentiable while at the same time being continuous, okay? And these kinds of functions happen. A good example of a function with this kind of corner is an absolute value function. Here's an absolute value function, right? And they've got that signature peak, right? I flipped it upside down, but any absolute value function has some kind of v point, or this upside down v, where it comes to a corner. And from one direction, the function is doing one thing, and from the other, it's doing another. And it makes an abrupt change, though it does maintain continuity, okay? And so that's an important distinction. We can define things, and will define things eventually, called one-handed derivatives. And all that means is we do just look from one side or the other, right? If I was to go back to this function, even though the function isn't differentiable there, if I take that derivative limit only looking from below, I can come up with a notion of the tangent line to this side of it, right? And then I could do the same thing over here. And this still tells us information. How is this graph behaving as I approach this point from above or below is still pretty good information. But we'll save that for another time. Okay, that's it for this one. Thanks, everybody. I will see you next time.